Hello everyone. For this semester I am going to engage Unit 5, that is Electrical Instruments and Measurements. Okay. Now let us see syllabus of Electrical Instruments and Measurements. Here you can see syllabus includes condition for moving coil galvanometer to be ballistic and deadbeat. Then theory of ballistic galvanometer, charge and current sensitivity and their relationship, correction for damping, and the next concept is measurement of capacitance of a capacitor using ballistic galvanometer by absolute method. Then determination of self-inductance by relays method and mutual inductance by direct method with necessary theory. And the last two concepts are theory of earth inductor, determination of BH, BV and psi. We need to complete this entire syllabus in 7 hours, and we also need to solve problems for about 2 hours, and we need to complete this entire topic, that is electrical instruments and measurements, in 9 hours. Okay, before going to start theory of ballistic galvanometer, I would like to recall one simple concept, that is torque. Okay, now let us see what is torque. Simple, torque is a measure of the force that can cause an object to rotate about an axis. Here I will try to explain torque by taking one simple example. What I will do, I am going to consider one object and its one end is fixed, and I will call it as a axis of rotation. What I have taken? I have taken one object and its one end is fixed, and I have denoted it as a axis of rotation, and I am going to take this length, that is I am going to take this length as a vector r. This is the distance vector. Then what I will do, I am going to apply some amount of force, that is F. What I am going to do, I am going to apply some amount of force F parallel to the distance vector. This is first case. Then what we are going to observe? It is very simple. This object remains in same position. It is not going to move in any direction, or it is not going to rotate in any direction when I apply force parallel to the distance vector. Okay, fine. Now what I will do, I am going to take second condition. In second condition, what I will do, I am going to apply force in perpendicular direction. I am going to apply same amount of force, but this time perpendicular direction to the distance vector. Then what we will observe? Simple. This body changes its position, that is this object rotates at some angle theta. What we have observed? If I apply force in parallel direction to the distance vector, we have not observed any rotation, but when I apply force in perpendicular direction, then this object start to rotate. From this, what we can conclude? It is simple. Here force is not responsible for rotation. Something is responsible for rotation, that is nothing but torque. Here For rotation, which is responsible? For rotation, torque is responsible. Okay, now we can find, let us find equation for torque. To find equation for torque, what I will do, I am going to take same example, that is, this is the object and this is the distance vector r and this is the axis of rotation. Then here you can see that torque is equals to force into lever arm. To find this equation, we need to find lever arm. So what we need to do to find lever arm? To find lever arm, we need to extend line of force. That is, here we have applied perpendicular force. Then what we need to do? We need to extend this line of force. Then second point, we need to find shortest distance from line of force to axis of rotation. That is, we need to draw from axis of rotation to force line. This distance should be very short. It should not be larger distance. So what I will do, I am going to draw a line from axis of rotation to line of force, and this is the 90-degree angle and this is the theta, that is angle between distance vector and line of force, and this is the perpendicular distance of lever arm. Here from this figure we can find lever arm, that is r perpendicular. We can find r perpendicular from this diagram, that is, we need to write sine theta is equals to opposite side, that is r perpendicular divided by hypotenuse, that is r distance vector. Then r perpendicular is equals to r sine theta. Then here we have equation for torque is equals to force into lever arm. Then here we need to substitute magnitude of force, that is torque is equals to, you can see here, force into lever arm, that is F into lever arm is nothing but perpendicular distance. Then if you substitute these values, then we get torque is equals to F R sine theta. Here you can see that torque depends on force and distance vector and sine theta. Let us suppose if I take two cases, that is, for first case what we have done? We have applied force parallel to the distance vector, that is angle between them is theta is equals to 0 degree. For this case torque becomes tau is equals to 0, that is sine 0 is equals to 0, so torque becomes 0. And also for second case, that is we have applied force perpendicular to the distance vector, that is angle between them is 90 degree. In this case angle between them is theta is equals to 90 degree. Then tau is equals to, here you can see sine 90 is equals to 1. Then equation becomes tau is equals to F into R, that is torque, it depends on force and distance vector R. This is all about torque. Torque is a simple, it is a measure of the force that can cause an object to rotate about an axis. And equation for torque is tau is equals to force into lever arm, or tau is equals to F R sine theta, or tau is equals to F into R. torque depends on force and distance vector. Here finally what we have concluded that force is not responsible for rotation. For rotation, torque is responsible. Okay, now let us see another concept, that is couple of force. Here you can see couple of force is a couple consists of two parallel forces that are equal in magnitude, opposite in sense. It does not produce any translation, it only produces rotational motion. Here I will try to explain this couple of force by taking one example. That is what I am going to do. I am going to take one, that is I am going to consider one object and exactly at the center, that is axis of rotation is fixed. Then at the both end I am going to apply two equal forces, but that is two parallel forces in opposite direction. That is one I am going to apply in this direction, another in this direction. Then what we are going to observe, it is very simple. This object and this is the distance factor from axis of rotation, that is r by 2, and r by 2 is a distance factor from axis of rotation to this point. This is the force F, this is the force F. Then this body, here I am going to take same example. This is the object, this is the axis of rotation. When we apply two equal forces but in opposite direction, then this object rotate through an angle theta. Here we have already discussed that for rotation, which is responsible? For rotation, torque is responsible. So we need to find torque equation for this situation. So what I will do, I am going to take torque is equals to, this is first case. Here I have applied the force F in perpendicular direction to the distance vector r by 2. So this becomes r by 2 into F plus same. Here what I have done, I have applied force perpendicular to the distance vector r by 2 from axis of rotation. Then this equation becomes r by 2 into F. Then this becomes F into R. Again in couple of force, torque is equals to F into R. This is responsible for the rotation of an object. Okay, we are going to use this couple of force to to study ballistic galvanometer. We need to remember this concept. Here what we have done, I have taken one object exactly at the center, that is axis of rotation is fixed. Then what we have done, we have applied two parallel forces but in opposite direction. Then this is the distance factor r by 2 between force F and axis of rotation. It is also same. This is the distance factor r by 2 between distance factor and force F. Then we know that torque is equals to force into distance vector. That is, here distance vector is r by 2, this is the force, so it becomes F into r by 2. Then here from axis of rotation to force, distance vector is r by 2, so I have substituted r by 2 value and magnitude of force. Then I have simplified. Finally I have get this equation, that is tau is equals to force into distance vector. Okay, Now let us study construction, working, principle, theory of ballistic galvanometer. Okay, now let us see what is ballistic galvanometer. Here you can see that this is the ballistic galvanometer device, which is used to measure small amount of currents or magnitude of currents. Here you can see the definition or statement of ballistic galvanometer. Ballistic galvanometer is a device that is used to detect small electric currents or measure its magnitude. Okay, then now let us see construction of ballistic galvanometer. You can see this is the block diagram of ballistic galvanometer and this is the actual ballistic galvanometer. Now let us study construction of ballistic galvanometer. Here you can see that the first point, the moving coil galvanometer consists of a rectangular coil that having n number of turns of insulated copper wire wound on a non-magnetic rectangular frame. Here you can see that in block diagram, this is the moving coil which is made up of copper wire, and you can see I have captured some photos from actual ballistic galvanometer. This is how the moving coil looks. Here you can see that this is the non-metallic frame and above non-metallic frame a copper wire wounded. This is the moving coil. Next point of construction. Here you can see that concave magnets are used to produce radial field. You can see these two are concave shaped magnetic poles. These concave shaped magnetic poles produce radial field. I will try to explain what is radial field. Let us suppose these two are two magnetic poles, that is north and south, and these are the magnetic field lines. These magnetic field lines are parallel to the plane of the moving coil. Let us suppose this is the moving coil, then these magnetic field lines are going to be parallel to the plane of the moving coil. We are used these concave shaped magnetic poles because these concave shaped magnetic poles produces magnetic field which is parallel to the plane of the coil, copper coil. Here you can see that concave shaped magnetic poles are used in actual ballistic galvanometer. Here also you can see that, and these are the magnetic poles which are used in the actual ballistic galvanometer. Okay, now let us see next point of construction. Here you can see that the coil is free to rotate about a fixed axis. A phosphor bronze strip that is connected to a movable torsional head is used to suspend the coil in a uniform radial magnetic field. Here you can see that the coil is free to rotate about a fixed axis. This copper coil, it is free to rotate about its own axis, about fixed axis. Then a phosphor bronze strip that is connected to a movable torsion head. Here you can see that this is the phosphor bronze strip which is connected to the copper coil. Then this movable torsion head is used to suspend the coil in a uniform magnetic field. Then you can see this coil is placed between two magnetic poles which produces radial magnetic field. Here in actual ballistic galvanometer you can see that this is the phosphor bronze strip which is connected to copper coil. Then upper end of the phosphor bronze strip is connected to torsion head, and this coil is placed between two magnetic poles. Okay, now let us see next point. Here you can see a cylindrical soft iron core is symmetrically positioned inside the coil to improve the strength of the magnetic field and to make the field radial. Here you can see that exactly at the center of the copper coil, a cylindrical soft iron core is placed. It is placed to increase the strength of the radial magnetic field. Here you can see that in actual ballistic galvanometer, this is the soft cylindrical iron core which is placed between the copper coil. It is placed because it increases radial magnetic field strength. And the next point is the lower part of the coil is attached to phosphor bronze spring having a small number of turns, and you can see the lower end of the coil is connected to the phosphor bronze spring which is having less number of turns. Here also you can see that in block diagram, this is the phosphor bronze spring which is connected to the lower end of the coil. Then the other end of the spring is connected to binding screw. You can see that other end of the spring is connected to the binding screw, that is T1. Now let us see construction once again. Here you can see that it consists of two concave shaped magnetic poles which produce a radial magnetic field, and in between these two poles a moving coil, that is copper coil, is placed, and exactly at the center of moving coil a cylindrical soft iron core is placed, and upper end of the moving coil is connected to phosphor bronze strip, and a mirror is attached to the phosphor bronze strip. Then upper end of the phosphor bronze strip is connected to the torsion head. Then lower end of the coil is connected to the phosphor bronze coil which is having a less number of turns. Then this spring is connected to the terminal T1. Okay, this is all about construction of ballistic galvanometer. Okay, fine. Now let us study principle of ballistic galvanometer. Here you can see that principle of moving coil galvanometer or ballistic galvanometer. It states that torque acts on a current carrying coil suspended in the uniform magnetic field. Due to this, the coil rotates, hence the deflection in the coil of a moving coil galvanometer is directly proportional to the current flowing in the coil. Okay, what principle states? Let us suppose the copper coil is placed between two magnetic poles which produces magnetic field of magnitude B. Let us suppose current I flows through copper coil. When current passes through this copper coil, what happens? It experiences force, and we can find this force by Fleming's left hand rule. Here you can see that this is the direction of current and this is the direction of magnetic field. Then this gives direction of force, that is, this is the direction of force. And here also say, you can see that current vector and magnetic field vector, this is the direction of current, this is the direction of magnetic field, and direction of force is into the board. Here you can see that two forces are acting. One is into the board and another is out of board. And here what happens? The current vector and magnetic field vector are both parallel. So the resultant force is 0 here and here. But at these points, the force is not 0. Here what happens? Two forces are acting on copper coil. Due to these two forces, what happens? Let us suppose this is the copper coil and a current I flows through this copper coil, and which is placed in a magnetic field, and magnetic field lines are parallel to the copper coil. Due to this coil experiences two forces, one into the board, another out of board. Due to these two forces, it experiences a torque. Due to this torque, what happens? This copper coil, it changes its position from its initial position, that is, it rotates from its initial position. So this rotation, it depends on the amount of current which flows through the copper coil. Greater the current, the greater the rotation we observe. Let us suppose less amount of current passes through the copper wire, then we are going to observe less rotation. So what principle states that when a torque acts on a current carrying coil suspended in the uniform magnetic field, here you can see that here a torque acts on a current carrying coil which is placed between the two magnetic poles. Then due to this, the coil rotates because of these two parallel forces in opposite direction. The coil rotates from its initial position. Hence, the deflection in the moving coil galvanometer is directly proportional to the current flowing in the